desk here. Right. So last Friday, I just did the ISBN 10 numbers. Yep. So I did ISBN 10 numbers. If you weren't there on Friday, a couple of people weren't. I'll put up the video of that at some stage. In the meantime, I'm going to try something a little bit different. Okay, we'll do it that way. All right, let's see if I can find a camera. All right. I can find a camera. That's good. So I'll share this with you. Camera. So this is basically lecture 27, and the idea about this again is the difference between codes and ciphers. So what we're doing now is part of coding theory, and coding theory is where we take a message, and we want to encode it in such a way that it can be safely transmitted, and safely meaning with as few errors as possible. So we certainly don't want to hide it. We just want to safely transmit it, or as opposed to securely transmit it. So we want the least corruption as possible. So the broad idea is that something like this. I talked about, so the broad idea is we've got a message that we want to get from the sender to the recipient, and things can happen to the message on the way. So the first thing we do is yes, I am indeed. I was successful in finding the camera. I thought I said, oh, okay. Oh, good. Thank you for that. Yes, I found the camera. I said share screen, and that's the second time today that's happened. Somehow, when I go to within Zoom and I double click, it doesn't register the second click for whatever reason. Okay, so we have a message. We want to get it from a sender to a recipient or receiver. And the idea is that we encode it into the thing that actually will be sent. And usually that encoding is using zeros and ones. Then we send the string of zeros and ones to the recipient. The recipient receives it and then decodes and gets the message back. So unlike encryption, we actually don't, we're not trying to hide it. All we're trying to do is get it from here to here with as few errors as possible. And a lot of it's based around a very simple idea. So, I mean, you've seen this sort of thing. If I write this, so if I write that, you can actually read it, and if you know it's supposed to be English, you can see that I've left quite a few letters out, basically all the vowels, and you can see that this says this message is redundant. So I don't know if the message is redundant or if the writing of the message is redundant, but you can leave out a whole lot of stuff and still recover what the message is. So what we want to do is sort of build in the redundancy into the encoding procedure. So one way we can do this is, suppose we just want to, I talked about this before, suppose the message is 0, and I want to make sure that 0 gets to the other end. One really simple thing is that instead of sending 0, I actually encode it to 0, 0, and then transmit that. So the person at the other end receives 0, 0, and they decode it to 0. Or I want to send 1, and I encode it as 1, 1. I send it, they receive 1, 1, decode it, and read 1. Or if I want to send 0, 1, 0, what I actually do is I encode it into 0, 0, 1, 1, 0, 0. Send it, they receive 0, 0, 1, 1, 0, 0, and they know because of the encoding system, they decode it to 0, 1, 0. This is not a great system because while there's redundancy, I can't actually recover necessarily the message because, you know, if the receiver receives this, what are they to make of it? Was that meant to be 0, 0 or a 1, 0? Was that meant to be 0, 0 or 1, 0? This is probably 0, 0. So what would be better is if we, instead of doubling, we tripled. So you encode, here's the message, you encode it into that, you transmit it, it gets received at the other end as 0, 1, 0, 0, 1, 1, 0, 1, 0, 0, 0. And the person at the other end says, well, given that we're sending in groups of 3, and given that I've got 2 zeros and a 1 there, I'm going to decode that as 0. Given that I was expecting either 0, 0, 0 or 1, 1, 1, what's more likely to have been sent? Well, or meant 1. 0, 0, 0, well, that probably corresponds to 0. So you're taking a short message, padding it out, building a redundancy into it so that as it gets transmitted, if anything gets corrupted along the way, you can have a fair chance at recovering. Certainly, even if you were a bit dubious about decoding it to 0, 1, 0, you could at least say there's definitely an error. You know, you've detected an error here. And you would have some idea of what that error might be. So that's really what's going on. The other thing is that here in my example, I'm just thinking of two just reading ahead a bit. Okay, so when I do this sort of thing, that 0 gets encoded to 0, 0, 0, and 1 gets encoded as 1, 1, 1. What I'm thinking about is sending this or this. Or if my original message is a sequence of zeros and ones, then I send a sequence of triple zeros or triple ones. We call these things code vectors. Okay, so this is a code vector that corresponds to, if you like, the message 0. This is a code vector that corresponds to, if you like, the message 1. Okay. Now, strictly speaking, vectors, we should write them with commas. in between. But sometimes we won't bother with the commas. So really, that's in a sense what's starting to go on here. Sometimes these are called okay. So something like this, you can't see it. Something like this is called a binary vector. So if we don't actually use it for coding, we just call it a binary vector. It's basically a list of bits. So it's got 1, 2, 3, 4, 5 bits in the list. First bit, second bit, third bit, fourth bit, fifth bit. That's really what vector, in some sense, means. That's a binary vector of length 3. This clearly has length 5. And as I said, sometimes we'll just abbreviate it like that without putting it into the brackets and the commas. So what we're going to do is use these binary vectors as the things that we're actually going to transmit. And when we do that, we'll have a collection of them. So this way. So here's a collection of binary 1, 2, 3, 4 binary vectors that each have length 4. Each of these is going to represent, if you like, a simple message. So what we have now is what's called a binary code. So it's simply a collection or a set of binary vectors, all the same length. That's important. And these are the individual things that we will send. So it'll be that, or that, or that, or that, or some combination of those. And the trick is encoding our message into these things. The other thing that we want that's very desirable is that we see that an error has been made. So if we receive, suppose the person at the other end receives 1, 1, 0, 1. What are they to make of it? Well, they know something has gone wrong because that's not one of the possibilities that could have been sent. So they know straight away. So here's our ability to spot if an error has occurred. So it's exactly the same as I did up here. These would be my binary code in this case, very simple one, would be 0, 0, 0, 1, 1, 1. It's a set. It's a set. That represents 0, and that represents 1. If I receive 0, 0, 1, I know something has gone wrong. Why can this happen? Well, there's all sorts of interferences that can happen. Radio frequency interference. Your CD is made up of zeros and ones. As soon as you have a mistake, you want the music still to play, or you're transmitting a JPEG file. Some of the bits get corrupted. You still want to recover the picture. The JPEG file really is just a big lot of zeros and ones. So we'd like to be able to recover things or see where an error has occurred. So this slide was just what I was starting to talk about. You might have the 2 bits 0 and 1, which we encode as code vectors of length 1, and you just hope that nothing happens to them at the end. If you simply decide to send 0 and 1 as 0 and 1, encode 0 as 0 and encode 1 as 1, there's no way of detecting an error because, you know, the person at the other end, if they receive 0, they have no idea if an error has occurred. So it might have been 0 and nothing happened, or it could have been 1 and there was an error. You just can't tell. Whereas if we encode 0 as 0, 0 and 1 as 1, 1, well, at least we have some chance of detecting. So here's the message 0, encoded as 0, 0. You receive this group, one of those groups. Well, even if you can't decode it because it isn't in it isn't in the list of things that could be received or could have been sent, at least you know that there's been an error. So with this doubling up, 0, 0 and 1, 1 as the two code vectors, we can detect a single error in transmitting 0, 0, and you can detect a single error in transmitting 1, 1, but you can't detect if there are 2 bits. So if the person wanted to send 0, they encoded it as 0, 0, they transmitted, but something happens in the middle, and 1, 1 is received at the other end. What's the person to make of that at the other end? Well, they have no idea if 1, 1 was sent and received correctly, or if 0, 0 was sent, but there were 2 bits. So there's no way that they can detect a 2-bit error within the code. So person at the other end receives 1, 1, they have no reason to suspect any errors have occurred because that's a legitimate thing in the set of things that we're allowed to send. Now, the other thing about 0, 0 and 1, 1 is the following. The number of 1s in this is 2. The number of 1s in this is 0. This is an example of what's called a parity check, because the parity means the number of 1s, or whether or not the number of 1s is even or odd. So if you had, if your code vector was 1, 0, 0, 1, that's got parity, even parity, because there are 2 of them. If you've got 1, 0, 1, 0, 1, 1, 1. Okay, there's a code of length 8, but it's of even parity because there are 1, 2, 3, 4, 5, 6 1s in it. On the other hand, 1, 0, 1, 0, 1, that has odd parity. So a lot of these things revolve around having an even number of 1s in each code. So this is an example of a parity check code. There are 2 things that we could send, 2, if you like, 2 code letters, if you want to think of it that way. So each of these corresponds to a letter. So it's an error detecting code that detects 1 error. Triple repetition codes. Okay, so instead of sending a single 0, triple it up. Instead of sending 1, triple it up. So there's a triple repetition code. You can detect 1 or 2 errors, as we've discussed. But if 3 errors occur, well, what could happen if 3 errors occur? If you transmit that and 3 errors occur, the other person will receive 1, 1, 1. And since that's a legitimate thing to have sent, they probably have no reason to expect that any errors have occurred. But if 000 was sent and 110 was received, then you know that either one or two errors have been made. Either that bit was changed and 111 was meant, or these two bits were changed and 000 was meant. That's what we mean about detecting up to two errors. Now, the problem with these repetition codes is, if you want to send a message that's 10 bits long, then you actually have to send 30 bits altogether, because you're doing this repetition, either 000 or 111. So there's always a trade-off. And the trade-off is that if you want to encode things more securely to guard against corruption in the transmission process, then basically you have no choice except to make the thing sent longer. Okay, pretty easily. If you've got 1, 2, 3, 4, 5 in your repetition code, then you can detect up to 4 errors. If you had 7, you could detect up to 6 errors and so on. But it's pretty inefficient. Having to send 5 bits instead of just 1 is not very sensible. So instead of just thinking about sending 0 or 1, I suppose we divide up our message into bits of size 2. So suppose our actual message is that's our actual message. So instead of encoding 1 bit at a time, what we might do is encode 2 bits. So divide it up into 2s. So we'll take 0, 0 and we'll encode it as something and send that. And then we'll take 1, 0, encode it as something and then send that. And we'll take 1, 0 again, encode it and send it. And we'll take 0, 1, encode it as something and send that encoding. Then take 1, 1, encode it as something, send it on. So that's what we mean by 2-bit messages. We're basically taking the string that we actually want to send. Instead of sending, if you like, a code for each bit, we'll send a code for each pair of bits. And that ups the efficiency. So really what we're thinking of is that there are 4 things that we could send, 0, 0, 0, 1, 1, 0, or 1, 1, and then just string those together to make the big message. So since there are 4 things, then our code has to have at least 4 vectors in it, 4 code vectors, 1 for each of these. When we just had 2 things, our code vectors just had to have 2. Now you can do the obvious thing. If you want to send 0, 0, just send 0, 0. If you want to send 0, 1, just send 0, 1. Encode it as 0, 1. Again, what happens if your message is 0, 1, you encode it as 0, 1, you transmit it, you get 1 error. Well, how would you decode 1, 1? Well, since 1, 1 was a possible code to be sent, you just decode it as 1, 1. So 0, 1 could get incorrectly received as 1, 1. So basically, again, there's no error detection capability. I mean, there's no way of seeing that an error has been made. One possibility is we take care of the 4 possible messages, 0, 0, 0, 1, 1, 0, 1, 1, and we make up a code of 3 bits, which basically counts the number of ones. So this is, it's called a parity check. code. So you add a check digit. So instead of sending 00, we're going to send 000, and we're going to append that extra bit. Why 0? Because we want the number of ones in our encoded vector to have an even number of ones. Okay, 0, 1. How can we make that into an even number? Well, by plonking an extra 1 on the end. 1, 0. Okay, there's only 1, 1. So how do we make it into an even number of ones? We'll plonk a 1 at the end. 1, 1 already has an even number of ones, so we append 0. So this last thing is kind of like a check digit. It's 0 or 1 to make sure that there's an even number of ones in the actual total code vector. So now if I receive 1, 1, 1, I know something has gone wrong because it's got an odd number of ones in it, and it can't possibly have been one of the messages sent. This guy is called, can you guys see a blue box around his face?
Yes.
Yes. Okay.
Facial recognition.
Yeah, well, yes, there is some sort of facial recognition. Ah, yes, so there it goes again. I'm not sure I wanted it. I wasn't even aware that it was on. Oh, the things you learn. Okay. This guy's was called, he died 20 years ago, Richard Hamming. He was very, very famous in information theory and coding theory. And one of the concepts that he involved is, here you've got 4 messages that can be sent, and you encode them, one message by this code vector, another message by this code vector, another message by that code vector, and another message by that code vector. So we'll call this one C1, C2, C3, and C4. And you know, if just looking at C1 and C2, you notice that they differ in 3 places, and they're the same in 2 places. Okay, so they differ in the second bit, the third bit, and the fourth bit. So what we do is we say that the distance from this bit, from this vector to this vector is just how many bits are different. So the distance from C1 to C2 is 3. So it's kind of like a function. 2 code vectors go in, and the distance between them comes out. So now we have, suppose we've got 4 messages. Each message is encoded by these 4 different codes that can be sent. Now what we ask ourselves is, what's the smallest distance between any 2 pairs of them? So the distance from C1 to C2 is 3, because there are 3 bits different. The distance between C1 and C3 is 3, again, because the 3 bits are the first, the third, and the fifth. The first, the third, and the fifth. The distance from C1 to C4 is, well, actually now there are 1, 2, 3, 4. 1, 2, 3, 4 bits different. Okay, same thing from C2 to C3, C2 to C4, C2 to C2 to C3, 4 bits different. C2 to C4, 3 bits different. C3 to C4, 3 bits different. Now it's a bit tedious. Just be thankful we don't have 100 code vectors. So out of all those distances, we'll look at the one that's smallest. So what's the smallest? Well, the 3 is the smallest. So what we say is that's the minimum distance of the whole code. So the whole code is just the collection of the 1, 2, 3, 4 code vectors. There's a distance between any pair of them, or between any pair of them, and the smallest one is 3. So we say the distance of the whole thing, or the minimum distance of the whole thing is 3. And it turns out, that gives you an idea of how many errors can be detected. Okay, so here's our 4 code vectors corresponding to the 4 possible messages we can send. You know, the distance, the minimum distance is 3. What's the significance? It means that if you transmit, or if you convert a message into one of these codes, transmit it, and there happens to be some errors along the way, then the person at the other end can detect either 1 or 2 errors, can detect less than 3. And that's because to muddle up one of these to make it look like another one, you would have to have changed at least 3 bits, because that's really what this distance is about. So, where am I? Yep. So when I say that the distance, the Hamming distance between C1 and C2 is 3, it means that I have to change 3 bits. So if this gets transmitted and this gets received, then some work has had to be done. 3 bits have had to have been changed along the way. But if only 1 or 2 bits have been changed, suppose I send this, but I receive that, where only 2 bits have been changed, I know that's not any one of these, because to receive a legitimate code vector, I would have had to have changed at least 3 bits. Here, there are only 2 bits have been changed. So this minimum distance actually means something. It tells you up to how many bits you can detect as an error. So this code detects up to 2 errors, either 1 or 2, but not 3, because I could send this and receive that, and I wouldn't know that this was actually meant. So it can't be relied on to detect, as many as 3 errors. And the same sort of thing for any sort of code. If you've got a code where the minimum distance between any pair of vectors is at least 4, okay, so we won't actually say what those vectors are, but if you've got a big code, the minimum distance between any pair of vectors is 4, then you know that you can detect up to, but not including 4 errors, so 1, 2, or 3 errors. If you've got a code with a whole lot of code vectors in it, and the minimum distance between any 2 of them is 5, then you can detect up to 4 errors, but not 5, and so on. So I mean, it's pretty straightforward. Why? Because this minimum distance is the minimum number of bits that need to be changed to get from any code vector to any other code vector. Oh, sorry about that. So we say that if the minimum distance of a particular code is D, then we can detect up to D minus 1 errors, but we can't detect D errors. We can detect up to 3 minus 1. 3 minus 1 is 2. So we can detect 1 or 2 errors, but not 3 errors, because if 3 errors are made, we might end up with one of these, one of the legitimate code vectors. Okay. All right. Okay, so we've got these 1, 2, 3, 4 code vectors. We've got those 4 code vectors. You want to find the minimum distance. What you need to do is just manually go through. What is the distance from here to here? Well, distance from this one to this one is actually 3. The first bit's the same, but the second is different. The third bit's the same, but the other last two. So the second, the fourth, and the fifth are different. So there are 3 bits different. From C1 to C3, okay, 4 bits different. C1 to C5, 3 bits different. And you can go through the remaining pairs. As I said, that's in a sense a bit tedious. Just be thankful you don't have 100 code vectors. What's the smallest distance between any pair? Okay, well, it's 3. So it means you've got to make at least 3 bits change to get from any one to any other one. How many errors could be detected? Well, at most 2. Now, this is not saying we know what the errors are, only that we can detect that the errors have been made. So this is really saying what I said before. I suppose, where is it? Here's the message that I want to send, 0010100111. What I do is I break it up into 2-bit segments. I encode so that there are 4 possibilities. I can either send 00, 01, 10, or 11. These are the messages. I encode each of these messages by a different code vector and then send a separate code vector for each pair of bits. Or I could do 3-bit messages. The idea is I take the same message, 001, 10, 010, 011, 011, and the final one, and I divide it up into the 3, and maybe I'll pad it out. Now, what are the individual messages I could send? Well, I could send 000, 00, that I want to encode, all the way up to that. So there are 8 different possible things that I can break it up into. And again, so here are the 8, 000, 001, 010, 011, all the way up to 111. Then I do this parity check digit thing. So it's like the checksum. I'll add a 4th bit to make sure that the number of 1s is even. So I've got 3 zeros here. There are no 1s, that's already even. So I put a 0 at the end. I want to send 001. I'm going to add the parity check. Okay, there's only 1 up to this point. So I've got to add an extra 1 to make the number of them even, and all the way through. So when I take this message, 001, so this whole thing, instead of transmitting 001, what I do is I transmit 0011. So this 001 gets encoded as 011. And 010 gets encoded as 0101. The 011 gets encoded as 0110, and the 100 gets encoded as 1001. So instead of sending this string, I actually send a string that's a little bit longer. So I send the message I send the string 0011, 0101, etc., etc. And the person at the other end divides it into 4 and recognizes, oh, this actually represents 001. This one represents 010. This one represents 011, and this one represents 100. So they recover the message that was actually intended. And that ensures that we can detect some errors. What's the Hamming distance here? Okay, so if you look through from there to there is 2 bits, from there to there is 2 bits, from there to there is 2 bits. In fact, the smallest number of bits you need to change is 2, so that the minimum distance, I can't spell today, minimum distance is 2. So how many errors can you detect? Well, 2 minus 1. So you can detect 1 error. I'm missing a page. Oh, there we are. Okay, so here's another example. Again, we've got 8 vectors. This one would correspond to encoding 000. This one corresponds to 001. This one corresponds to 011, all the way down to 111. But what we've done is we've added 2 extra bits. So instead of sending back here, we've got, here's my message broken up into 3s. I need to encode 001. Well, I'm actually going to send 001. 011. Sorry, actually, I'm adding 3 bits, not 1 bit. So I take the 3 and I add another 3 in a particular way. So the person at the other end receives that, but knows that 001 was intended. Okay, big question. How many Hamming distances have to be calculated? Well, we've got 8 possible code vectors. So from C1 to C2 to C3 to C4 to C5 to C6 to C7 to C8. So that's 1, 2, 3, 4, 5, 6, 7 of them. Then from C2 to C3, I don't have to work out from C2 to C1. I've already done that. The distance from C2 to C3, C2 to C4, all the way down to C8, well, that's 6. And you go through, what you see is that there are going to be 7 plus 6 plus 5 plus 4 plus 3 plus 2 plus 1. Okay. 7, 8 was 28, I think, something like that. So there are lots of distances involved, and the minimum amongst all of them is 3. So if I use this as my coding, then I'll be able to detect up to 2 errors. But I've had to extend my code vectors out to length 6. And again, the idea is that here is the actual message that I'm intending. I divide it up into 3s. I encode each group of 3 by the equivalent code vector, and then actually send the code vectors. In all of those, we've added extra bits. So we've basically put some redundancy in there by adding the extra bits, whether it's 1 parity check bit or Like this one, where we're adding 3 bits. So this message has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 bits. But if I encode it using this scheme, I'll actually have 24 bits, so double the length. But the point is that I can then actually, the trade-off is that by doubling the length, I can now detect that some errors have been made in the transmission. Okay, that was a fair bit today. So we'll leave it there. And when do we meet again? Thursday, is that right? Yep, Thursday. Okay. Now, actually, yep, Thursday. Okay, so we'll see each other on Thursday. All being well. Stop sharing. Yep, cheers. So, see you on Thursday.